Welcome back to Gradient Daily. Today, we are breaking down a paper that forces a recalibration of open-source machine learning, Tencent's newly published HunyuanVideo. State-of-the-art video generation is currently dominated by closed systems. Models like OpenAI Sora, Runway Gen-3, and Luma 1.6 operate behind proprietary APIs, where their internal mechanics remain hidden from the research community. This lack of transparency creates a bottleneck. Without access to weights or training logs, the open-source community cannot easily iterate on architecture or diagnose the specific reasons for physical inconsistencies in generated frames. Tencent's HunyuanVideo represents a move away from that model. It is a 13 billion parameter foundation model with its weights and training framework released under an open-source license. The authors provide data showing that this model matches or exceeds the visual quality and motion dynamics of its closed-source counterparts. This level of performance was achieved through 4 specific pillars: aggressive data curation, a specialized diffusion transformer architecture, progressive model scaling, and optimized distributed infrastructure. Scaling to 13 billion parameters was only one part of the equation. By providing a high-fidelity baseline that researchers can actually modify, the paper offers a direct, transparent alternative to the proprietary systems that currently lead the field. At its core, HunyuanVideo utilizes an advanced diffusion transformer engineered for latent spatiotemporal processing. This architecture manages a complex requirement, parsing text prompts and random noise into stable video without dissolving into visual noise. A specialized spatiotemporal attention mechanism handles this by continuously intertwining individual spatial nodes with cross-attention connections throughout the entire temporal timeline. Imagine a CNC machine cutting a block of material. Carving a 2-dimensional shape on the X and Y axes represents spatial framing, but calculating the Z axes, the depth of time, requires the system to map physical constraints as the machine moves. If the machine loses track of the shape's parameters from 1 millisecond to the next, the object warps. This approach also secures the text-video alignment. The semantic intent of the prompt is anchored to the temporal axes, preventing the subject from mutating. Treating time as a mathematically entangled dimension allows the architecture to eliminate temporal flickering and physics breakdowns. The strength of the architecture is dependent on the quality of the inputs. In large-scale video training, dataset quality is often a more significant constraint than compute availability. The researchers began with a massive, unstructured pool of web video, typically riddled with artifacts and inaccurate captions. They refined this raw material using a process similar to fractional distillation, filtering the crude input before it trains the diffusion engine. The first stage of filtering uses automated scoring for aesthetics and motion. This removes static, blurry, and low-quality clips, ensuring the model learns from high-contrast data. A second filter verifies text-caption alignment. This ensures physical actions on screen are accurately reflected in the semantic descriptions used during training. The team specifically prioritized sequences containing cinematic techniques, such as pans and rack zooms. By preserving complex physics, they taught the model consistent camera movement. Training a 13 billion parameter model on low-quality data leads to consistent hallucination. This rigorous curation process results in the model's benchmark-leading performance. A common question in model training is why a system cannot be trained at full HD resolution and high frame rates from the very first step. It comes down to gradient instability. Initializing a massive network with high-complexity data frequently causes the learning process to fail. The solution is progressive model scaling, a phased approach plotting training epochs against increasing resolution. Similar to metallurgical annealing, early epochs use low-resolution clips to establish a broad semantic baseline. Gradually, resolution and clip length increase, integrating fine details and complex physics. Coordinating 13 billion parameters across these phases required a specialized distributed infrastructure. The system was designed to handle the load across thousands of GPUs without the memory fragmentation that stalls large-scale training. Progressive scaling ensures the model maps base semantics early, creating a stable foundation for the high-resolution features added later. This training stability is reflected in empirical data. Benchmarks provide final validation of the framework's effectiveness. When compared directly to Runway Gen-3, Luma 1.6, and leading regional models, HunyuanVideo consistently performs at or above the level of its proprietary competitors. These results were confirmed by professional human evaluators. They focused specifically on how well the video followed complex text prompts and whether motion dynamics remained plausible. The data highlighted specific areas where HunyuanVideo performed well, particularly in maintaining consistency during long camera movements and achieving high compute efficiency during inference. Reaching these levels through a transparent open-source methodology indicates that architectural precision and data quality produce results matching well-funded proprietary labs. There is a practical trade-off to this scale. Running inference on a 13 billion parameter model requires significant hardware resources, making it a heavy lift for individual developers or smaller labs. This highlights the current questions surrounding scaling laws. The community will need to identify where the diminishing returns of parameter count begin, especially as the hardware requirements for video generation continue to climb. However, because the code is open source, researchers can bypass the multi-million-dollar cost of training the base model from scratch. They can immediately begin fine-tuning the existing weights for their specific needs. We expect to see community adaptations using LoRa, specializing models for niche fields, ranging from high-accuracy fluid simulations to temporal interpolation for medical imaging. While the computational requirements are high, the availability of HunyuanVideo provides a foundational baseline for the next phase of open-source video research. Reviewing the main findings, a 13 billion parameter open-source model has successfully reached the performance levels of the leading proprietary systems. Second, the refinement of training data through curation is as essential to the model's success as the architecture itself. And finally, progressive scaling is the key method for balancing clear semantic logic with high-resolution, complex motion. If you value these technical breakdowns of the research driving AI development, like this video and subscribe to the channel. Join us tomorrow for the next research paper deconstruction on Gradient Daily.